So here we are. This is a talk on teaching biology to undergraduates, teaching undergraduate biology students.
That's right. So I hope everyone can see my screen.
Yes.
All right. So let me, again, I have a presentation. I'm hoping there'll be enough time for I can show some of the materials, but I wanted to just go through the logic carefully. And so that a lot of words, not so many pictures, but I'm hoping I'll have time to actually show you some of the teaching materials. So let me see here. Oh, I see what I have to do. Hold on. And okay, there we go. So I'm going to talk about the challenges and opportunities that are presented by dealing with biology students, particularly, what the educational goals of my course are, why I chose to do the textbook that the way I did, the course structure, and then in the first half of the semester, the kind of background I give my students so that they can do the second half, which is to actually reconstruct and extend models that were published in the technical literature describing biological systems, and then say a little bit about the student projects that have been recently done, and then summarize and conclude and take any questions that people might have. So I think anyone who's had interactions with biology students has some clear sense of how they view math and programming. And I can say from my years of experience, with many exceptions, but largely these are students who chose biology because they don't like math, physics, or programming. And they hoped that they could actually get through their career not having to deal with it at all, if possible. There are exceptions, so this is not a rule, but this is typical. And the reason is, and again, people have talked about it, there are books on this, these topics often generate a great deal of anxiety in these students and give them a feeling that they're incompetent. I joke with them that probably their experience of math was a way of convincing them that they were idiots. The thing that's striking, however, is that it's not because these students lack intelligence. They actually have very strong and deep understandings of complicated biological systems. And if you talk to them about biology, they're quite competent and they have deep understanding. And the thing that's also striking is that modeling is a helpful tool for understanding biology. So if there were a way of getting them into this, it would be very helpful. Now, the other challenge, and because CASE is outstanding as a school for pre-meds and also as a school for people who are interested in engineering. So I get a number of very good students who are from math, physics, and engineering backgrounds, and their view of biology is sort of the mirror image. They think of it as the memorization of structures and arbitrary names and abbreviations. And I unfortunately feel that way myself to some extent. And that there are no clear principles or abstractions that can be deducible from first principles. And yet, and this is increasingly true, that there are fascinating problems in biology that would reward someone who knew how to do modeling. So how do we deal with this? So the educational goals I stated at the outset and that I had for the course was to allow the students to learn to create dynamical models of biological systems, to analyze these numerically and mathematically, to extend the models to address new questions, and then to write about the models clearly. And I state these at the outset of the semester. That's what the course is about. So for my textbook, I looked at various things and I read, I just want to have a shout out to Kurt, by the way. One of the reasons that I got invited here is I ordered it. There were some problems with it, so I got to talk with Brian, which was actually a wonderful experience. He's very helpful. And I'm enjoying reading the textbook very much. But then I shared with him some of the stuff I was doing. He says, oh, you should come and talk to us as well. Anyhow, but one of the things I've always been concerned about, that textbooks are not interactive. And I want the students to be able to directly manipulate the material and see what happens when they do that. Also, I'd like them to be able to just steal the code that I've written and directly take it into their own place and use it immediately. Because again, that lowers the barrier for them to be able to do it themselves. And I wanted to be able to seamlessly integrate text, equations, and graphics. So at the time I did this, starting in about the beginning of the 2000s, the only game in town that had all that was Mathematica. Now I might do something using Python and Jupyter Notebooks and Colab, but that wasn't available at the time. So the whole book is written within Mathematica. I make it freely available to the students to download. And this is a link, which I can also put in the chat, But the latest version, my course is available on Canvas, and I've set it up so that you won't have access to it unless you're a case student in terms of grades or submitting assignments, but you can actually go and look at the syllabus and download all the material if you follow this link. So the course structure is the following. I have the students working in teams of 2 because, as I tell them at the first half of the semester, there's only going to be one other person in the class who's going to care about the model you're reconstructing in the second half of the semester, and that's your teammate. And it's a lot less lonely if you have somebody to work with. I evaluate the students separately. My experience and their experience with teamwork is that if you have 2 students and you give them a shared grade, then one person does all the work and the other person kind of stands by. This way, we let them work together and talk to each other, but we evaluate them separately. And we keep checking to make sure that they're doing their own work. Technically, just to understand how much time the class meets Tuesdays and Thursdays, 75 minutes each time. And in the first half of the semester, the students get the background they need to understand and recreate models. And what I do is I have them do their assignments in Mathematica, and the notebooks with those assignments are due a half an hour before class. This allows me and my fellow instructors to go through what they've done and then have an educated discussion with them. At the beginning of class for 15 minutes, I give a brief mini lecture, usually about something that they're going to need to do for helping them solve a problem that they have within a class session or another. And then the rest of the time, we just talk with the students. So I sit for usually about 15 minutes apiece, which means I can talk to 4 teams or 8 students. And over the years, I've been able to raise up a coterie of undergraduates who've taken the course, and the department is willing to let them be paid so that I can have them as fellow instructors in the course, which means we have 32 students in the class. And the focus on these conversations is conceptual understanding, not just did you get a graph, do you get a right answer or a number, but do you understand what you did? Now, in the second half, with our guidance, they choose papers from the technical literature, and they reconstruct the models, and they have to put together these, what we call term paper benchmarks, which I'll describe in a little while. And let's see, can I? Oh yeah, that's the problem. There we go. Okay. Sorry, the Zoom thing is in the way. All right, back to here. Then one of the things that we do is that the instructors meet for an hour after class to discuss student progress and to assign points. And so this way, if someone is a fairly harsh grader or someone is a very lenient grader, the students always see roughly the same assessment, and we rotate so that every 4 classes, the students get to see all the instructors. And the focus is on student progress, and especially if we think a student is falling behind, is having troubles, we try to send emails to reach out to them, and we provide office hours throughout the week. Okay, and so this is just a picture of what the classroom looks like. It was remodeled in 2008. We have these 6 hexagonal tables. The students sit at them so they can actually interact, and the teaching assistants move from team to discuss results. During the pandemic, this all became on Zoom, but fortunately this year we were able to go back. I'm at the age group where I wear a mask, and I encourage the students to do so when I'm sitting and talking to them, and other than that, they can do what they like. But this is the kind of interaction that goes on in the classroom. Okay, so in the first half, on the first day of class, what I do is I start off by, so to speak, warning them what's going to be happening, because I think it's not fair to students to not let them know what you're going to be planning to do. Gonna have to move this out of the way, apologies. And go back to here. Yeah, so I talk about the rationale for modeling. A lot of biology students are somewhat puzzled why they should even be taking a course on this topic. The engineers and physicists and mathematicians don't need this, but it's important to articulate this. And I tell them that if they take this class seriously and work hard, they will be going essentially from novice to expert in just 1 semester, which is it's a hard claim to make, but it's a self-contained course. I give them the background they need, and if they really work hard, they're actually going to be engaged in modeling research by the end by extending a model that they've reconstructed. I go through the educational goals I just listed. I tell them the structure of the course and how it's going to be assessed. And then there's a whole chapter that I have on mastering the fundamentals of Mathematica, which is the guidebook that Mathematica doesn't have because it's all these atomic pieces of description about how to use particular commands and never how to put it all together. And so that chapter allows the students to go through and actually see how you could use it for practical purposes. I then have a chapter which starts with showing some pictures of bacteria and saying, gee, it looks like every so often each bacteria has two daughters. So let's set up an iterative recursive model. Basically, f of n plus 1 is equal to 2f of n. And that's not a very good model, as I show by comparing it to the data. So I say, gee, it looks like bacteria continuously divide. How would that look like? And then we actually come from the discrete to the continuous, and we have a model of exponential growth. And then we compare it and talk about the future and show, after you fit the parameters, it works for a while and then it fails because the bacteria stop growing. They just hang out there. And that gives us the basis for developing the logistic model, because there are some issues in the environment that are changing the bacteria growth. So they see an iterative process of how you can build a sequence of models in order to better and better understand a particular biological system. And the key point is that the failures of models are as interesting as their successes, sometimes more so, for figuring out what you should do next. This, of course, with the logistic and the exponential, we have two fairly simple one-dimensional dynamical systems. And so I can introduce them to the concepts of trajectories and flows, and global phase portraits and bifurcations in that rather simple way. And I was delighted to see that Kurt had the transcritical bifurcation, because that's what I do in that chapter. And then in the problems, they get to do a saddle node bifurcation in one dimension. Then there was a model developed by Tyson and Novak on the cell cycle, where they said that there were particular checkpoints the model had to go, that the system had to go through. It's a two-dimensional model, and it uses all the different pieces of chemical kinetics: 0th order, 1st order, 2nd order, and Michaelis-Menten kinetics. It's a wonderful, simple model, but it allows you to then go on to two-dimensional dynamical systems, show the phase plane, and actually show them and have them build a saddle node bifurcation in 2 dimensions. And then I have a chapter on modeling neuronal activity, and that allows me to talk about oscillatory behavior spirals, eigenvalues with complex components in the Hopf bifurcation. And that basically takes us to the end of the first half of the semester. They've seen generic bifurcations, they've seen some differential equations, they've seen what I've called modeling motifs, the kinds of things you'll see in a lot of the biology models and the differential equations. Now it's time for them to choose a paper. So in the second half of class, they have to work with us to select a paper to reproduce. They have to make a term paper proposal, which describes the hypothesis that will be tested, based, of course, on the paper, and then what particular parts of the paper they'll reproduce, and then what ideas they have for extensions. And I'll talk a little bit more about that. And then at the beginning of the second half of the semester, they have to have a model plan, and they have to have intermediate goals and a timetable for what they're going to do. And then I have them hand in 4 benchmarks. After about a week, an introduction to their paper. A week later, a model description. By now, they've reproduced their model, and so they're writing a term-by-term model description where they explain each of the terms of the differential equation and what they mean in terms of the biology. They should be able to do. 2 weeks after that, the results without the extension. And then a week before the thing is finally due, a discussion. And then we meet with the students in the second half during every class to provide suggestions. Now, we also meet out of class to assess student progress. And one of the other things we do, which we don't tell the students, is that we only accept papers that we think we can reproduce ourselves. And during spring break, we build at least the first 2 or 3 figures from the paper for ourselves. So we are able to give these strikingly useful comments about how to reconstruct the paper. We also discover, and this is painful, because there's very little vetting of mathematical models, fully 30% of published papers are probably absolutely irreproducible. There are missing parameters, no initial conditions, there are typos in the equations, they're a disaster. And we don't want the students to fail because the paper cannot be replicated. So this is a problem in the technical literature we have no control over. But by doing some of this work in advance, we can head it off at the pass. And we sometimes do have to tell students to change a paper when we find it's impossible to reproduce. We then, in the last 2 weeks, encourage them to work on extensions to their models. So that can be changing parameter values. that can be changing the shape of the model, that can be doing additional dynamical systems analyses that were not done by the authors, but they're actually doing some kinds of original research. And then we have students volunteer for the last 2 classes to give presentations. We give them officially 10 minutes, but we schedule 15 minutes, which is why we can handle 5 student presentations in each of the two classes. So about 10 teams get to present. 3 points extra credit out of the 100 that you can get for the semester. I should mention 50 for the benchmarks in the first half, 50 for the term paper, and then this is 3 points extra credit. So they're strongly motivated to do it, and they do usually an excellent job. And then the final term paper is due on the last day of class, which we tell them on the first day of class, and I reiterate, and I have a fairly strict late policy since they knew about it from the beginning of the semester. Now, the reason we have them hand in the benchmarks is that instead of their opening up a file the night before and starting to write the term paper, I was a procrastinator, so this is why I've introduced this into my class. This way, they are strongly encouraged to have written large parts of the paper. And at the very worst, they can cobble together these pieces and have a pretty decent term paper. And at the best, of course, they can really make it much better. And so we also insist that each student write his or her own term paper. And that's very interesting. Sometimes people are great coders, not great writers. And so it forces all the students to get to a certain level of mastery. Okay, and then the student projects, just examples of what students worked on last year. Cancer is very popular. And people know why, and the growth of it, control of it, various kinds of chemical or radiation treatments. There are various papers on mathematical models of that. Naturally, COVID-19 featured, but there are also HIV infections, avian flu, Ebola. A nice paper on the closing and opening of the Venus flytrap that used differential equations, and models of inflammation like neutrophils and macrophages and their interactions. And then one that took in neural inputs and then generated models of excitation, contraction, coupling in muscle and skeletal muscle force. And I just should mention that one student has actually published a paper in the technical literature based on this course. Her name was Priscilla Ambrosi. She was doing research on Drosophila development, and she reproduced a model that Canodi et al. Had created of Drosophila development as part of this class. And then working with Claudia Mizzutini, she used this to address a question about Drosophila development, and this was published in PLOS Computational Biology. And many other students have come after taking this course and talked about that they've lost their fear of being involved in the modeling, and they're more interested in it and so on. So let me just summarize the key points here. If you give appropriate guidance and support, biology students can master the tools and techniques necessary to understand, reproduce, and extend mathematical models. And math, physics, and engineering students can also master extraordinary amounts of complex biology in the context of mathematical modeling. Then they actually start, if they have to understand what this term means in terms of the T cell behavior, they actually spend time understanding what T cells do. Providing the necessary intellectual support for students and regular feedback to ensure their success is very time intensive. I just have to emphasize that before everybody leaps off and says, oh, we should do this too. It's very time intensive. On the other hand, it is extremely rewarding for both the instructors and the students. And giving the students the ability to master interdisciplinary material and write clearly about it provides them with skills that can help them throughout their careers. And science had this competition on inquiry-based instruction. Our course actually won that award, and we were able to publish a paper about it. So this is an article in Science called Learning Biology by Recreating and Extending Mathematical Models. And the supplements give even more details. As I said, the chapters of the book are available. And that was all I wanted to say formally. I think I have time, if people permit me, to just, is that good? All right. Let me just show you the one or two of the chapters, and let me see if I can stop sharing and then share my screen so that you could see one of the chapters. Okay. So this was chapter 3, modeling growth and iterative process. I hope you can see it. Now, the way Mathematica works is that you can create these groupings of cells. So you can see the entire, this is the table of contents, but if I click on this, I actually see the content, which is, here's some bacteria, they're growing. Here, I'm able to set up a Recursive model, I set the assumptions that bacteria divide at the same time and they divide after a fixed doubling period. That gives me a recursive model. I discovered that if I just run it without initial conditions, I get an infinite loop. So I already learned something that you have to set up initial conditions. So once I do that, I now can get something that actually works. And I can then plot it after fitting the data, and I can see to what extent it fits the data. And what I spend some time showing them that you can actually prove that this is simply the same as 2 to the k. If we just compare it to the data fitting the parameters, so I spend some time doing that, we see that it's not a great model after the first 2 doublings. And that leads us to realize that the model has failed. So under those circumstances, it might be useful to come up with a new set of assumptions, like that bacteria divide continuously and at some average time. And if you do that, what you can do is, instead of dividing only at the end of the doubling period, they could divide halfway through, or a third of the way through, or a quarter of the way through. And lo and behold, you get this really interesting expression, 1 + 1 over n to the n, which if you take the limit is e. Cool. So that's introducing the exponential growth model and also showing it as a simple differential equation. And now let's try to fit that to the data. So we do that. It does a little bit better, but it's still not great. What happens if we have lots more data from bacteria that have grown over longer periods of time? If we take the logs of that, we get this kind of thing. And if we use the model properly set up, and I show them how to do linear regression and getting the appropriate parameters, you could fit the model to the data, and that looks really pretty good. So I say, well, okay, that's a nice fit. Have we gotten done? Well, let's predict future behavior. Let's just expand out and go a few more hours, and we have data for it. And if you compare the model to the data, you see that it does well for a few hours and then it fails miserably. And that's because the bacteria can't grow endlessly. And so now you have to define limits on population size. And so you readdress your assumptions. You add the rate at which bacteria divide decreases with the number of bacteria present. You could have, and I have them do as a problem, the number of divisions becomes equal to the number that die. Turns out the equation is the same. Anyhow, that allows me to show them, if you take that linear change in growth, that you can actually set up the logistic equation, which you can actually solve. And that does a much better job. And again, we extract the parameters, we compare it to the data, it looks good. And then I say, what's going to happen next? And it turns out the students have to think about this, but what's going to happen next is the next point is going to be down on the x-axis, because with no new nutrients, all the bacteria die, which is not the prediction the model makes, but is what happens if you run out of nutrients. So I emphasize in this chapter that really the way to think about it is that if you're going to do this, you should think about models not as the absolute best thing, but as a useful first approximation. And then you go back to the biology, you compare it, and you see how you can make the model better. And if you start with a simple enough model, it actually tells you which things need to be added in and what you should change, which is extremely helpful. So I emphasize that that's what they should do, and that then that's the then they have several problems, and that gives them a chance to further understand this material. Anyhow, so that gives you a feeling for what each of the chapters does. And again, I mentioned that, for example, the modeling the cell cycle one allows me to do chemical kinetics, modeling excitability does oscillations and so on. Anyhow, so I just wanted to share that with you. Any questions about anything I had to say here?
I have one.
Please, Joe.
That was beautiful. Quite an amazing example as well. You mentioned fitting the model a number of times. How do you do that? You have some tools that you're using in Mathematica to do that.
Yes. Yeah, so Mathematica can do linear curve fits, and it can do linear regression. It knows how to do that. See, one of the things that makes Mathematica so helpful and powerful here is you can conceptually describe the idea, and then instead of having students compute sums of squares and all the stuff that we used to have to do, I still remember slide. When you actually just have them put in a command to do linear fit, and it will come out with numbers, and then you can plot them to see if they're reasonably good. You can also look at residuals to see how good the fit it actually is. So you give them the conceptual thing, and then the tool is very powerful, and then they can actually do a lot with it.
Okay. Do you run into problems of identifiability with any of the models that you use?
That's a big problem. And again, the issue is I introduced the concept of free parameters. I introduced the issues that when you do modeling, you have to be very careful, because sometimes you could use several different, there are several almost equivalent equations that you could use to capture the system. And some of them are going to be much more tractable to analysis than others. And I emphasize there's some art involved. I also tell them that this is not the last course they should take in this area, and that if they overcome their fear and anxiety, there are many, many really good, more advanced courses that I can encourage them to take so that they learn parameter estimation and system identification, all the key things. But the problem is, if the group you're dealing with are frightened of the material, you're never going to get them into those more advanced courses. So my goal here is to make it self-contained and make it relatively painless to get to a point where they feel some mastery.
Well, it seems like you've been very successful with that. Yes.
I would say that in every semester, there are often one or two students who really struggle. The vast majority are reasonably content, and there's several students who actually fall in love with the material, which I think is great.
Yeah.
So I would say that based on the anonymous student comments, you can't please all the students all the time, but you can sometimes get most of them not miserable and some even happy if you work at it. So that's what I would say.
Great.
One comment about anxiety on the part of biology students for mathematics. In the 70s, the application for the University of Michigan Medical School has a box to check that says if you've taken a differential equation course. And I always used to tease the admissions, the pre-med advisors. Do you think that's because if you took it, they won't let you in? Is that why they put it there,
Again, because Case gets so many pre-meds and they're super concerned about their GPAs, many of them put off taking the physics and the calculus till their senior year. So if I had prerequisites for this course, I'd never see any of the students. So I have to work on the assumption the last time they saw any of the stuff was in high school, and they didn't like it.
About a year ago, I got a phone call from a former student of mine at Albion College who was a math biology major, who has a PhD, MD, and is the head of a 300-person unit at the University of Pennsylvania Medical School. And they were trying to use decoys to lure the COVID virus from attacking, hard stuff. And they were trying to build mathematical models, and he had teams on there, but he remembered the old Professor Winkle. And so I met with them for 6 months. I don't think their method was successful, but Jim was the one who pointed out the differential equation box on the Michigan, and he went to Michigan and knocked it out of the park. Well, I think you're very good at laying it out and supporting them all along, including the practical, don't put it off, and getting feedback all along and helping them with correcting a bad literature. So they're going to have a good experience. And I would suspect, even though you make it that they write it by themselves, you don't discourage them from talking to each other.
I want them.
It's
critical for them to talk to each other. It makes a huge difference. It's so lonely. I mean, part of the whole idea of doing it this way is that most of the biology students, their experience of a math course is they're alone in their dorm room. It's 10 o'clock. They have 5 other hours of homework to do. They're struggling with the problem set. They're getting nowhere. Absolutely nowhere. And they just feel like, why am I wasting my life doing this? And they sit down with a chemistry textbook. They sit down with their biology textbooks. They make great progress. They can get A's. There's no relationship between the number of hours they're spending getting nowhere versus how much they're getting out of it. If you change it so that the students are getting the support in the classroom from the mini lectures and from the conversations, that changes it. It's much less a feeling of, I'm overwhelmed, I can't do this. We still get some of that, but much less than when we did it. I initially had this as a lecture course, and I had great difficulties. And then I changed it in this way, and the students really benefited from that.
Yeah.
So we have one question that asks if you put some links about the course.
I'll do that, and I'll put that into the chat. If you
Yeah,
have-
I want to